Alright, so for this video I just want to go through two example problems with work, and we're keeping them simple, short, because we want to keep these videos down. So let's do two example problems for work. The first one is kind of conceptual problem, and I want you to think about this situation. A force is applied to a moving object, yet no work is done. How is that possible? So now we're thinking about a situation in which the work again is equal to the force multiplied by the cosine theta and then the change in our distance value. And what we're saying that yes, a force is applied. So we have a work of 0 and we have a force applied. Let's say it's just for fun 5 newtons. And we have cosine theta, and it says that the object is moving, so we know that we have a value in there for our distance value. So how is it possible that no work is being done? Well, I'm going to give you 30 seconds to think about this. So pause the video right here and think about what could be happening. Let's give a hypothetical number to our distance. Hey, let me erase. Let's give a hypothetical number to our distance of 13 meters. So pause the video right now and think about why or how no work could be done. Now, if you're a conceptual person, you probably can pick up on the answer right away. If you're not so much a conceptual person, let's have some fun and let's do some math. Well, if I divide both sides by 5 and 13, well, guess what? I'm going to get 0 no matter what. So now I've got, let's scroll down a little bit. 0 equals cosine theta. Okay, well, let's find the inverse cosine of theta. So cosine of 0 equals theta. Oh, oopsie daisies, theta equals 90 degrees. So let's jump up and let's look at this question again. It says a force is applied to a moving object, yet no work is done. How is this possible? Well, these would be situations in which the force that is applied applied at a 90-degree angle perpendicular to the surface. And so perpendicular to the motion or the displacement of the object. Um, and so a lot of times we might go back to the idea of the normal force and how much work does the normal force do. And let's jump to a new slide. Let's say that I have a kid going down a slide and, oops, the kid's going down the slide, yay. And as the kid's going down the slide, the displacement is going to be in one direction, and the normal force is going to be in another direction, really upward at a 90-degree angle. And so we see that this 90-degree angle is going to result in the work done by the normal force being equal to 0. So no work is done. No work is done by the normal force because the angle is equal to 90 degrees and the force is perpendicular to the displacement. So that's that first kind of example I want to go through. The second example is going to be a little more math intensive. So grab out that graphing calculator. Let's jump to a new slide. So here's example number 2, and maybe you want to pause this and get this drawn out on your paper. But what we have is going to be a sled that's being pulled at a 20-degree angle, and we have the tension of a rope. We see that the mass of the sled and maybe the person on it is 26 kilograms. The coefficient of friction is 0.16. The distance they're going to travel is going to be 120 meters, and the velocity is constant at 3 kilometers per hour. Now, the fact that I just said the velocity is constant really should make like an alarm go off in your head that goes, something important. Because whenever the velocity is constant, that means something really huge. That means that the forces are balanced. When the forces are balanced, we now get to do some really simple stuff. But forces balanced, that's huge. Make sure whenever you see constant velocity, your brain should automatically go to, okay, that means that the forces are balanced. What can I do from here? No, we're not going to need this until later, but let's really quickly find the weight of the sled. So we're going to take the mass of 26 and multiply by 9.8. That'll just be useful for later. So weight is equal to 254.8 newtons, and that's just going to become useful later on in this problem. Now, let's first find the tension of the rope. We're going to do three things, and I'm going to Let's write down what we're going to do here on the left, and then we'll just start solving away. First, I want to know what is the tension. Then I would really like to know what is the work done by the person that's pulling this sled. And then I would like to also know what is the work done by the ground itself, by friction. So I've got these three questions I want to consider. What is the tension? What is the work done by the person who's pulling the sled? And then what is the work done by the ground to oppose that work? And the fact that it's in a constant velocity should already get in your brain tinkering about a few of these and what their values will be. Let's go to a new slide and let's first start talking about the work or about the tension. Now, because it's at a constant velocity, that's really a big deal because it tells me that the forces are all balanced. The forces in the horizontal and the forces in the vertical are going to be balanced. And so as you look at your drawing and you think about the horizontal forces, what we really have acting on the sled that are balanced forces are going to be the force in the, or the tension in the horizontal direction. And what's going to be resisting that motion is going to be the kinetic friction. Now you may be saying, wait a second, why did you write this equation like this? This is really just an abbreviation already of the sum of the forces in the x are equal to the tension, which is causing the object to move, subtracted by the force of kinetic friction. I just wrote it differently, which will be nice for the math later. Let's think about the vertical component now. In the vertical component, we have the weight working downward, and then we have the normal plus the force or the tension in the vertical direction. Those two add up to equal out the weight. Well, we can begin to simplify a few things right of the way. We know that this situation, we have the block getting pulled at this angle. So if I want to find the tension in the x, I want to find the tension in the y, and I am ultimately looking for tension. What I can do is kind of consider the right angle trig. So Katoa. And if I want to find the angle in the, or the magnitude of the tension in the x value, I'm going to go cosine theta multiplied by the tension is going to be equal to the force of friction. Jump over to the vertical side. I can do the exact same thing. Weight is equal to the normal plus sine theta multiplied by the tension in the applied tension. Well, let's take it one step further and let's even simplify out our force of friction. So our force of friction, if I want to continue to substitute things out on the horizontal side, I have cosine theta multiplied by the tension is equal to the coefficient of kinetic friction multiplied by the normal. Well, ooh, I want to combine these two equations, and I finally found a variable that these two share. The normal force is a variable that these two share. And so what I can do is I can take my horizontal equation and I can make it equal to n so that I can substitute everything in for n. How handy. So all we need to do here is we need to get the coefficient of friction over to the other side. Stop, Sherry, this is where you need to fix the video. It's 841, so now that I've found values that are equal to each other, the normals on both sides, what I can do is I can take my vertical data over here, I can make it equal to my normal, and then I can plug that in for the horizontal data. So all I have to do is subtract sine theta multiplied by the tension over to the other side so that I have that n is equal to the weight subtracted sine theta multiplied by t. So I subtracted sine theta t over to the other side, and then I just kind of rearranged the question. I can now take this whole little buddy right here, weight subtracted, weight minus sine theta multiplied by the tension, and I can plug that in right there. So I'm going to get a new helpful equation. Cosine theta multiplied by the tension is equal to the coefficient of kinetic friction multiplied by the weight minus sine theta t. Okay. Whew. Next, I want to redistribute my coefficient of friction. So I'm going to have cosine theta t is equal to coefficient of friction in the K multiplied by the weight minus the coefficient of friction multiplied by sine theta multiplied by t. Now ultimately we want to solve for t, so let's move the time or the tension value over here on the left. Let's move this whole segment over to the other side, which will allow us to eventually simplify for tension and give us a little bit of an easier equation. No, let's pause right now for a second. And you may be saying like, oh my goodness, this is the type of question that's so intense. Quite honestly, this is your free response style question. And when you see a question like this, yes, you're going to be relying a lot on understanding what's causing and what's hindering motion and how to then rearrange the equations to fit what you're solving for. And while you may be having like a bit of a headache right now as you're solving for this question, all we're doing is truthfully taking our horizontal data and our vertical data, finding the fact that they have the normal value in common and substituting those in, and that's allowing us to solve for the tension. Once we have the tension, we can find work. And so again, we're going to add the cosine or the coefficient of friction multiplied by the sine theta of t over to the other side. And now what we're going to get is a very nice new equation that is cosine theta t plus coefficient of kinetic friction sine theta t, and that's going to be equal to something nice and simple like coefficient of kinetic friction multiplied by the weight. Now I don't know about you, but I'm ready to plug some numbers in. So let's plug some numbers in really quick. Cosine 20 degrees is equal to, or multiplied by tension plus 0.16 sine 20 degrees multiplied by tension 0.16 multiplied that weight. Oh, remember when I told you that weight would be useful? Let's jump back a few slides. How do I jump back a few slides with this bar in the way? Okay. The weight, 254.8. 254.8 multiplied by 254.8. Oh, this is so awesome. Now I can do some simplifying and get some math going here. It'll make this a little bit cleaner. Feel free to pause the video and do the math ahead of time if you'd like. So just so you know, when we get the tension finally, the work questions are going to be so easy. So stick with me on this one. We've got 0.94 multiplied by tension plus 0.055 tension equals 40.77. Let's simplify this side, and what we're going to see is that tension is equal to 0.94 plus 0.055, which essentially is 0.995. All I did was add these two values together to get this value, and that's going to be equal to 40.77. Divide both sides by 0.995, and we get a tension value of about 41 newtons. Holla. All right, so now we're ready to actually do some work. And that's in the physics sense, ha ha ha. So we've just solved for number one in our question. What is the tension? Now let's go through and let's look at number two. What is the work done by the person? Okay, new slide. Work done by the person, well, that's going to be work is equal to the force multiplied by the distance. Now, here's the tricky thing is we're thinking about the distance that's going to be in the x component. So we need to find force in the x component. So really, this equation already has to be rewritten because if I remember, it's the box being pulled at this angle. Just found that tension value there, but I want to find the tension in the x so that I can actually solve for this question with the work in the x. So in order to do that, I'm going to have to do some right angle trig. And you know, you'll get better at remembering which values go with which, and some people are awesome at it already. But for this value, for the force, we're going to be thinking of cosine theta multiplied by the original tension. So it's a force, but we're going to just make it a T right now for tension. Hey, the tension multiplied by the distance traveled. And so if I rewrite this again, it becomes cosine 20 degrees multiplied by 41 multiplied by 120. And that gives me a work value of around 4,623 joules. Now, I'm realizing right now that we never talked about what the units are for work. Hey, they're joules. I hope you remember that from last year. But they're joules, and it's spelled a fun way. J. Oh. All right, units for work. Now, to save on time, we're going to skip solving for the work done by friction, and we're going to talk about this on our own time a little bit more. But I have a big idea I really want to make sure that I share with you right now. This is a big idea, and then I'm going to wrap up this video. This big idea is the fact that it's traveling at a constant velocity. And so as a result of traveling at a constant velocity, that tells me that the forces are balanced. And this should be a little bit of a review. That means that the forces are balanced. Well, if the sum of the forces equals zero, which is another way to kind of think about this, if the sum of all the forces equals zero, then all I need to do is plug that into my work equation to find out something very intriguing. So my work equation is, again, work is equal to the force. We're going to keep the cosine theta in there, but it's also then multiplied by the change in the distance. And hey, if force is equal to zero, for like the total force, then that means that the total work done is also equal to zero. And so this is like talking about the work totes is going to be equal to the F net, which in this situation would be zero, cosine, doesn't matter what the theta is, doesn't matter what the radius is, because the work totes here is equal to 0 joules. Intriguing, intriguing. So if it has a constant velocity, that means the forces are balanced, which means that the total work done on the system is going to be equal to 0 joules. Okay, well in this example that we did with the sled being pulled problem, the total work would really be equal to the work done by the person plus the work done by the friction, by the ground really. And if the total work is equal to zero, and I told you from my last page that the zero, and I told you that from the last page that the work done by the person is 4,623 joules, I bet you can figure out how much work is done by friction. I'm just going to leave it right there, and like, if you get lost right here, come find me ASAP. But I think you can actually find that value, and I believe that you can do it. I believe in you. Have a great evening. Bye.